Okay, so for number 7, sorry, the video got cut off. We know that it's going to be still going to the left, but it's going to be slower because when these two hit, it's giving some of its momentum to this guy to turn around and go the other way, so it means it lost some of its momentum. So the only one that shows it moving negative, staying negative, but getting slower is C, because I have a negative value, and then I go up to a less negative value, so still negative, but less velocity, slower, so C. Alright, now number 8. It says, we have 3 balls, all with equal mass. They're all attached to a string and free to move. B is at rest, and then A and C are both moving towards ball B with the same speed, V. So going at V and negative V. Ball A and C hit this ball at the exact same time, but what's different is that A and B stick together, whereas C bounces off and goes back the other way. It bounces off of ball C and goes back this way. And we want to know that these two that are now stuck together, which direction do they move? So the easiest way to think about this is conservation of momentum. If these are all equal masses and they have the same velocity, then the total momentum beforehand was 0. So that means the total momentum after has to be 0. Well, no matter what velocity this one goes off with, it's going to the right, so that means you have some positive momentum. Let's say it went off at B. I don't know that it did, but let's say it went off at B. Then if this one is going to the right, then these two, which are stuck together, have to go off to the left because momentum has to be conserved. Now, it would be going at a slower velocity because the two of them have to cancel out this momentum, so it would be like V over 2. But we don't need to do the actual velocities. If this one is going to the right, these two have to go to the left because momentum has to be conserved. That's the easiest way to think about it, so your answer is to the left. Another way to think about this is the impulse that these are delivering to one another. So when this one comes in and bounces off, that's giving a big change in momentum because let's say I went off at V, then the change in momentum would be the 2mv because I come in at V and I go V the other way. That's a change in velocity of 2v. Whereas this one, when it comes in, isn't going to deliver because it's sticking. It can't go off at the same velocity, V, so it has less of a change in momentum, or less of an impulse. So that means that when this one hits, it delivers a greater impulse to this ball than this one delivers. So it hits it harder. You can think about it as harder with the force this way, and then this one's force this way. So then it ends up going this way. Or you can think about the first explanation, which probably makes more sense. 9, a car on a freeway collides with a mosquito that's initially at rest, and then you can assume that it hits the mosquito and then the car continues driving. Does the total momentum of the car-mosquito system increase, decrease, stay the same? It has to stay the same because momentum is conserved. Did the momentum of the mosquito increase, decrease, or remain the same? Well, it was at rest, and now it's going to be moving with the car, so it increased because it got faster. Momentum of the car increased, decreased, or remained the same. Well, the total momentum stays the same, and this one increased in momentum, so that means the other object must have decreased. You also can think about it is whenever this one hits this second mass, and then now it's going to give some of its momentum away so that the mosquito is now moving with the velocity. That means it lost some of its momentum because it gave it away, so now it's moving a little bit slower. Obviously, not much slower, pretty much negligible, but the idea is it technically slows down a tiny, tiny bit amount, so it would decrease in momentum. Which changes its speed by more in the collision, the car or the mosquito? Definitely the mosquito, because you can, if we were to make up numbers, let's say this was coming in at a velocity of 100. Now it slows down and is now at 99. This guy gained 99, whereas this one lost -1 in its velocity. Now if you're like, wait, but they have to change by the same amount. No, velocity is not conserved, momentum is. Which is why, I'll talk about that in E. Now another way you can think about this is the acceleration, because your change in speed will determine is determined by your acceleration, the rate at which you're changing speed. So they have the exact same force on each other, but they have different masses. So the smaller mass, when you divide by a smaller number, you get a greater acceleration, so therefore a greater change in speed. So the greater change in speed is a mosquito because it has less mass. E, which changed its momentum by more, it has to be the same amount because momentum is conserved. So if this one loses, I don't know, 10 kilogram meters per second, the other one must gain 10 kilogram meters per second because it is conserved. Back what I was saying here, if you're wondering like, wait, but it changes its speed by a ton, right? This one's changing its speed by, let's say, 99. This one was only changing its speed by 1. How can they have the same change in momentum? Well, because this one has a lot bigger mass than the mosquito. So the small mass changes by a big velocity, the big mass changes by a small velocity, so you can still bounce out to the same amount. And it has to be the same because momentum is conserved. Greater impulse, well, the change in momentum is the exact same. Remember, impulse is change in momentum, so if they have the same change in momentum, they have to have the same impulse. Which one has a greater magnitude of net force? Has to be the same net force because the force of the car and the mosquito is the same force as the mosquito on the car. It's the same force. It is between them. Newton's third law. Another reason impulse would be the same is if you have the same force for the same amount of time, then you have the same impulse. So basically, change in momentum, impulse, which are the same thing, are equal because force and time are equal, but the change in velocity and the acceleration are different if they have different masses. A 5 kilogram toy car rolls down the ramp. It starts from rest at a height of 0.8 and it hits another stationary car with a mass of 3 kilograms. So when this one comes down, it's going to hit this 3 kilogram car. So basically, we've got a 5 coming in at some velocity, hitting a 3, and then they have Velcro and they stick together, and I want to know the velocity after. Well, in order to find the velocity after, I need to find the velocity of the 5 kilogram when it comes down to this level surface. So we're going to use energy. Right here, kinetic energy is 0 because it's released from rest. Down at the bottom, potential 0 because you're on the ground. So it only has kinetics. That means that mgh is going to go all into 1/2 mv squared. The mass is going to cancel out. You can plug in the 5, it doesn't matter. 10 height of 0.8 equals 1/2 b squared. This is 8 is 1/2 b squared, so 16 equals v squared, so v is 4. Remember, that's not your answer. That's the velocity that this one's coming in with. Now I've used my energy to find its incoming velocity. Now I need to find the after velocity of the collisions. We're going to use momentum. So momentum before, this one's at rest of 0, is equal to momentum after. These two going at the same velocity because they're stuck together. That's 8v, and then you get that your velocity is, what is it? 2.5. 11, 2 pucks attached by a spring initially held at rest on a frictionless surface. The pucks are then released simultaneously, meaning at the same time. Puck 3 has 3 times the mass of puck 1, and then when they are released, they spring apart like this because there's a spring between them. What do we know about their momentums? Well, the total momentum before was 0 because they were initially at rest. Momentum is conserved. There's no external forces. The internal force of the spring is on both of them, so that doesn't count. So my total momentum still has to be 0 after, so that means they have the same momentum, just opposite directions. And the reason they have to be the same is because you need them to cancel out to 0. So it's impossible to have like positive 10 and negative 8 cancel out to 0. It would have to be positive 10 and negative 10, or positive 8 and negative 8. They have to be the same but opposite to cancel out to a total of 0. Now their velocities will not be the same because if they have the exact same momentum but different masses, by definition they have to have the different velocities. So let's think about, you know that this has to be the same for both of them. So let's say we want the one that goes fastest. The fastest one will be the smallest velocity, like this. So then puck 2 is going to go faster because it has the same p but less mass. So more velocity. 12, given the force versus time graph above, is the momentum increasing or decreasing from this time to this time? This is like time 0. Now, a lot of people look at this and they're like, the graph is going down, decreasing. Okay, but I didn't ask about what the force is doing. This is force and this is time. The force is absolutely decreasing. That's just not what I asked. I asked, what is the momentum doing? Well, force versus time graph, we can look at the area under the FT graph gives me the change in momentum. If we were to look at this, I I have a positive change in momentum. If you have a positive change in momentum, then what's happening to the momentum? It's increasing. Otherwise, you would be losing, it would be negative. So it has to be increasing because you have a positive change in momentum. And it wants to know by, also you can think about like this decreasing is when let's say I'm pushing, there's a net force of 10. So of course it's accelerating. Now I'm still pushing, I'm just pushing with a net force of 5. So it's still accelerating, it's just not accelerating as much. So not accelerating as much, but still getting faster, still gaining in momentum. And then again, only when it gets to 0 does it stop gaining in momentum. And then when it gets below, that's where you have negative, and that's where you'd be losing momentum. So it is gaining momentum the entire time, and then at the end it stops gaining. And I want to know by how much. Well, change in momentum is just area under the curve. So F naught times TF over 2, because your base times height over 2, because it's a triangle, so that is how much the momentum is changed by. A shell is moving eastward with a horizontal velocity of v naught, and it explodes in midair and breaks into 2 pieces. The larger one is like 3m, then the smaller piece goes west at 5 v naught, and I want to know what is the velocity of the center of mass. Well, this one's going to go this way, I don't know how fast, but it doesn't matter because center of mass is going to stay, the velocity of center of mass stays constant, so it'll just be the v naught that the center of mass was traveling at when they were together before. 30 kilogram object traveling at an initial velocity, and a varying force is exerted on the object, and the graph shows the data for force for a time interval. Which of the following is closest to the net change in speed, so the change in velocity, from 0 to 5. Well, force versus time graph, I can find change in momentum from area under the curve. We have to be careful here because when it's positive, it's just area under the curve. When you go negative, it's not under anymore. You're always trying to go to the x-axis. So you actually have to shade up here. Now we can just pretend this was a straight line. It's pretty linear. So I said this was like 200. So then 200 base of like 3 divided by 2. This one I said negative 100 base of 2 seconds divided by 2. So that gives me an area of negative 100, and this one an area of positive 300. So if you gain 300 and you lose 100, that means that you changed by a positive 200. So change in momentum is the 200. My mass is 30. So change in momentum is also mass times change in velocity. Divide over the mass, that gives me my change in velocity. Either way, I know that I end up with a positive change in momentum, so you can cross off A and C. And that's because, yes, I end up, or like in the end, I am losing momentum, but I gained so much in the beginning that I haven't even started, like I haven't got back to where I was, right? Gaining 300 and losing 100, you still gained. Divide over, you get 6.66. And if you, like, maybe you said that was 225, that's fine. You're going to get close to this answer. You would get close to this answer if you didn't show that this was negative. 15 kilogram lump of putty is moving to the right at 5 when it collides with a 0.25 that's initially at rest. What is the resulting speed after the collision? So this is an easy one. Just momentum is conserved, and they're stuck together. It's the same velocity. 7.5, yeah. Divide over velocity is 4.28 something. Does the kinetic energy increase, decrease, or stay the same? Well, first of all, you can actually calculate, so I didn't. You can plug in, find what the kinetic energy before is, and find what the kinetic energy after is, but you already know that it doesn't stay the same, because this is a stick together that's called an inelastic, completely inelastic collision, so you know the kinetic energy is not conserved. It's not gaining kinetic energy, it's losing kinetic energy, so without actually calculating the final and initial kinetic energy, we know that it's decreasing because that's what happens in an inelastic collision. Now, what happens to that energy? It goes to other forms. So sometimes it goes into internal energy in the object because like the object itself gets like crushed. sound, heat, etc. This graph goes for the next two questions. So we have the velocity of two identical carts. Identical is keyword for that they have the same mass. I mean, they have the same everything, but same mass here. And what looks like is happening is that you've got some positive velocity. Let's say it starts out at like 25, and then this one starts out at negative 20-ish. And then it's not like a collision. There's some, like, I don't know, something's happening in here. Maybe it's a collision, but that's a really long collision. So what's asking is there a net external force? So when you're asked, is there a net external force, and we're talking about masses and velocities, well, that's just saying, like, is momentum conserved? Because we know momentum's conserved unless there is a external force. So let's look. If they're the exact same mass, then then they should change by the same amount of velocity. Well, if you look, cart 2 goes from like negative 20 to negative 5-ish. So cart 2 has a change in velocity of positive 15. And if you have like, wait, I said change by 20, that's fine. It's not exact. And this one goes from 25 to, I don't know, 0. Maybe you said negative 5. I'm going to say like 0. So change in velocity for cart 1 is it loses negative 25. Now, it is totally possible to have two different change in velocities, but momentum stays conserved. That would be if this one had a bigger mass and this one had a smaller mass. But it had told me that they have the same mass, so the change in momentum for cart 1 is negative 25 times the mass, and the change in momentum for cart 2 is positive 15 times the exact same mass. So here, momentum is not conserved, which means there is a external force because momentum wasn't conserved. Now we have to decide, is it a positive or a negative external force? Well, overall, so like the change in momentum in total would be negative 25, positive 15m, that would be negative 10m. So I'm losing momentum overall in the system, which means that I must have a negative net external force, D. Now, for B, yes, it is true we have a negative net external force, but it's not because cart 2 decreases. If cart 2 is decreasing and this one increased by the same amount, like if they had met here and here, then there would be no net force at all. It's because the total amount of momentum in the system decreases. All right, 17, the velocity of the center of mass of a two-cart system at T0 was V. What's the velocity of the this one right here. I forgot that this goes with this. So right now, at T equals 0, the, did I put 6 seconds? This is so random. I meant like at the end. Why did I put 6 seconds? Anyway, the velocity at the end, what is the velocity of the center of mass at the end is what I meant to say. So normally center of mass velocity stays the same, but that's if there's no external force. So it's not going to be V because we just said that there was an external force. External force. It was a negative external force, so if I had some positive velocity and then I applied a negative force, that means it's going to slow down. Because I would have a negative acceleration with a positive velocity, so it's going to get slower. So the reason, and you had to get this one right to get this one right, actually. The reason this one is not just V is because we said there actually was a negative external force. So the center of mass would not continue at a constant velocity. Block of mass 5, it travels towards stationary cart of unknown mass. The cart and the block stick together, and this shows the velocity of the block, this one, both before and after. So no matter what's happening, when it hits a second mass, it's going to slow down, right? When these guys hit together, it's going to go a little bit faster, or a little bit slower than what it was. Now, how much slower it gets depends on like how big the mass is. If it hits a huge mass, then it's going to slow down a lot. If it hits like a tiny mass, right, it's barely going to slow down at all. So in this case, it slows down a lot. So you have a big change in velocity, which means you must have hit a big mass, so more than what it was. This one doesn't slow down very much. That means it hit a small mass, less than this guy. And here, you can't say it slows down a lot, you can't say it slows down a little. In fact, it gets exactly half, so you have half the velocity, which means you are hitting exactly the exact same mass as before. So let's say this came in at 4, which was that 1, 2, 3, 4. Let's say that was 4. Then afterwards, when they're stuck together, it would have to be at 2 to keep momentum conserved, because if you have double the mass, you just spread that momentum of 20 between the two, so they each go at 2. So exactly equal. 21, a proton mass M and a lithium mass 7M undergo an elastic collision, meaning Ke is conserved. What is the velocity after the collision? So remember, we have the special case where if they are the same mass, they just switch. They are not the same mass, so I can't just say this one stops and this goes off at V naught. That would be nice. So this is going to be one of those complicated where I have to set up 2 equations, because in an elastic collision, both momentum and kinetic energy are conserved. So let's start with momentum being conserved. I have mv naught, and then afterwards I'm going to have mv1 plus 7mv2. Now I can't say v and v because they do not stick together. In fact, I know they don't stick together, because if they stick together, that's an inelastic collision. It's not. So I don't know what's going to be happening. Probably this one goes off. I have no idea if they bounce off each other, so just unknown and unknown. If anything, we know this one's going to go this way. Whether this one bounces off or continues just slower, we don't know yet. So we can simplify this a little bit, cross off, so we have V naught is V1 plus 7 V2. Alright, that's my momentum conservation equation. Now I can go to my kinetic energies, still conserved. I started with 1/2 V naught squared, and then at the end I'll have 1/2 mv1 squared plus 1/2 7m v2 squared. So again, I can cross off all the m's. I also can cross off all the halves. So you've got v squared equals v1 squared plus 7v2 squared. Okay, now I need to combine these two, so we're going to use substitution. So I found it easiest to solve for v1, because then it's just v naught minus 7v2 is v1. And now I can take this v1 and substitute it in for v1. So I've got v naught squared is v1, which is now this, squared, plus 7v2 squared. Careful here, you can't just square each term. You've got to do like the box method or the FOIL. Whichever way you do it, you should be getting v naught squared minus 14 v naught v2 plus 49 v2 squared. That's what this term squared becomes. Remember, like this squared and this term squared are definitely in there, but you have these other two terms which combine to make the negative 14 v naught v2. And then that's still equal, and I still have a plus 7 v2 squared. So I'm going to subtract this over, so then that cancels out and is 0. These two add together, 56 v2 squared, and then I'm going to add this one over, so 14 v naught v2 equals this. Let me rewrite this. 14 v naught v2 equals 56 v2 squared. So we're trying to get the 2 by itself, because our answer is in terms of v naught. Well, I can divide by v2. That cancels out one of them, so now I divide the 56 over. 14 over 56 is just 3/4? No, 1/4, yeah. 1/4 v naught. So then we go to our thing, well, that we can cross off A and C, because the velocity 2 is the velocity of the 7m, so it's going at 1/4 v naught. But I need to know what the velocity of the other mass is. But that's really easy, because v1 is just v naught minus 7 whatever. So we can do v naught minus 7 v2, which was 1/4 v naught. So this is basically like 1 minus 7/4, so 1 minus 7/4. And then math enter gives me negative 3/4. So then v1 is negative 3/4 v naught, which is what we get for v. Object is pulled, starts from rest with a force probe for an interval of time. The force as a function of time is shown. Sketch the graph of momentum as a function of time. So this one is hard to get, like actually really good sketch. It's just a general trend. So first we are starting from rest, and starting momentum is 0. Now let's think about what's happening in the first second. So in the first second, we have an increasing force. So that means that my momentum would be increasing, because if I have a force at all, it's increasing. Also, remember, your change in momentum is just the area. So like in this one, right, my change in momentum in the first second was 5. Now, in the next second, I'm still changing momentum, right? I'm still increasing in momentum. Now I've gained a little bit more momentum, maybe, I don't know, you could say like average like 7-ish, or like 10, maybe like 10-ish, 8-ish. I'm not going to actually calculate because I don't really know what the average of that would be. It's kind of funky. But let's say I gained my momentum by 5 in the first second. Now I gained like a little bit more in the next second. Now in here, in the next second, I gained more than 10. So what happens here is people see constant and they try and make your momentum constant. Actually, I have more change momentum in this second than I did in any of the others, because I'm going at a steady constant force greater than any of the other forces. So of course I'm like accelerating more here than I was with the smaller force. If I'm accelerating more, I'm gaining more and more momentum. So, man, I'm really bad at drawing these, getting steeper and steeper. I'm going to redraw this. So I gained some momentum, I gain even more, and then I gain even more in this second. So basically it's getting steeper. I guess we could have tried to like draw it like curved and then it's like at a constant steep rate, but it's really hard to draw these on your own. But the big thing here is that your momentum is increasing the entire time. There's at no point does it decrease momentum, and at no point does it even go constant. It is increasing. Your graph should be going up the entire time. All right, number 2, these two collide, stick together. Which is the momentum of M before and after? Well, first of all, it starts positive. And then when these two stick together, because this one has more momentum to the left, it's going to end up going to the left. So I'm going to end negative, and it's going to be slower than before, because this one's giving some of its momentum away to the first object, so it has to be slower. So the only one that starts positive, ends negative, but slower is C. Starting positive, ends negative, but a slow negative. 24, spring between A and B is compressed, and the spring is released. They push apart, so this one goes this way. Object A moves at the speed of -3. Object B moves at the speed of 6. What does that mean about their momentum / their mass? Well, if they're initially at rest and then released, then their momentums have to be equal, because the total momentum is 0, what we were saying on the front with like puck 1 and puck 2. So the only reason, or only way that this one can go faster and have the same momentum is if it has less mass, D. So this would be like easy. If this is 6, then this one would still have a momentum of 18 and -18 to cancel out to 0. Which one has greater kinetic energy? Well, kinetic energy is 1/2 mv squared. This one has a greater mass, but this one has a greater velocity, but velocity matters more, so B. What is the velocity of the center of mass? Well, there's been no external forces, so the velocity beforehand, when they were all at rest, the center of mass was at 0, so it stays at 0. 25 goes with this graph, by the way. So I didn't write a description. You've got object 1 and object 2. So object 2 is going at 3 meters per second, object 1 is going at 6 meters per second, and then they stick together, and now they are both going at 4 meters per second. And I want to know how which one has a greater momentum, or greater mass, and to explain. So if you look at this one lost 2 meters per second, this one gained 1 meter per second, so they have to have the same change in momentum, because momentum is conserved, but they have different changes in velocity, which means they have different changes, or they have different masses. So the one that has the greater mass is the one that's velocity doesn't change as much. So 3, 2, 4, this was object, this is object 2. Object 2 is going at 3, and object 1 was going at 6. So the one that changed the least was object 2. So the greater mass is object 2, because it had less change in velocity. Remember, they're going to have the same change in momentum, same force, same impulse, same time, but they'll have different change in velocity because they have different accelerations based on their mass. The greater acceleration will go with the smaller mass, so the bigger change in velocity goes with the smaller mass, so the less change in velocity goes with the bigger mass. And what is true about the center of mass of the two objects? It's at rest. Well, afterwards, when they're stuck together, they both go at 4, so the center of mass has to be at 4. And the center of mass is not going to be changing. There's no external forces. It's just two objects colliding. even though I didn't give the description. Sorry about that. Yes, last page. Here, which one has a greater mass? So we've got object 1 going at a positive 5, object 2 going at negative 5, and then they both end up going to the right at 1. So if they're coming in at the same velocity, but they end up going to the right, that means this one had more mass to begin with because it had more momentum if it ends up going to the same direction as this one. So object 1 definitely has a greater mass. You could use that reasoning, or you could say because again it only changed its velocity by -4, whereas the second object changed its velocity by 6. That's another good reason. The greater change of velocity means less mass, and the less change of velocity means more mass. So object 1 would be your answer. A battleship fires a shell at A. The shell is projected to land at ship A, which is a distance d away from the battleship, but instead it explodes into 2 halves of equal mass. One lands 2d away. Where does the other one land? So the average of them, like the center of mass, is at an imaginary point. If this is half the mass, and then the center of mass has to be here, then the other half has to be right here. Because see how equal masses, equal distance apart, would cancel out to be the average in the center where it should have landed. So that means it landed on battleship. Because these have to be equal distance with the equal masses to average out to still land in ship A. Now, the next one, same situation, but now it's not equal masses. The less massive piece lands the distance 2d away. So here it's the smaller mass. So now I don't want to land like here because then it would be skewed over to the center mass would be skewed towards the greater mass. So that means the greater mass must have landed somewhere to the left of the ship because you still want it to average out, but it's closer to the ship than this one was. Not that my sketches to scale. Maybe something like this. Because see how the more mass, the center of mass is going to be closer to the bigger mass, so I still need my center of mass to be here, so the bigger mass must be closer, the smaller mass must be farther away. So it's somewhere between the battleship and ship A. And then a battleship, again, blah, 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 D, 2D away. But now it is the big piece. So if the big piece lands a distance d away from where it should have landed, then the small piece must be extra far away so that these can still average out to the same center. So the center mass has to be closer to the bigger mass and farther away from the smaller mass to still average out to center mass. Also, you can think about it, if this one, when they explode, this one's going to, obviously you're going to go opposite directions. This one is smaller mass, it's going to go faster than the bigger mass, so it'll go farther. That's another way to think about it. So to the left of the battleship. Okay, I hope everyone actually watched all that study hard.